students, here we are going to discuss about state space representation of discrete time systems. Here the analysis of the discrete time systems by using state space representation is similar to that of the continuous time systems. So in the case of discrete time systems, we are taking system with m inputs, p outputs and n state variables. So we can represent the state variables as x1 of k, x2 of k, x3 of k, etc. up to xn of k. Input variables are u1 of k, u2 of k, u3 of k and um of k. Output variables are y1 of k, y2 of k, y3 of k and yp of k. See, here the notations are similar in the case as in the case of continuous time system. In that case also we are taking input as u, output as y, state variables as x. But at that point we are in the case of continuous time system we are using t as a variable. Here we are in the case of discrete time system we are taking k as a variable. Okay, it represents the discrete instance of time. So we can represent the discrete time control system as, here the input is u1 of k to um of k, that is m number of input variables, and the state variables are x1 of k to xn of k, that is n number of state variables, and output variables are y1 of k to yp of k, that is p number of output variables. And the discrete time control system can be represented as a u input, y output and x state variable. So this is the state space representation of the discrete time system. So we can write these inputs, outputs and state variables in the matrix form as column matrix. So input vector is u of k, that will be a column matrix, and output vector is y of k, that is also another column matrix. State variable vector is x of k, that is another column matrix. Okay, so we can represent this discrete time system by using n number of first order difference equation. In the case of continuous time system we were representing it with n number of differential equations, but in the case of discrete time systems we are representing it with n number of difference equations. So we can represent the state variable as x1 of k plus 1 in terms of a function of state variable and input. So we can represent x1 of k plus 1 will be a function of f1 of x1, x2, etc. up to xn, and function of u1, u2, etc. up to um. So it is a function of state variable and input variable. So similarly we can write n number of state variables in terms of functions of state variable and input. So we can formulate a differential equation in terms of x1 and u1. So we can write a matrix for that. So in the matrix form the above difference equation can be written as x1 of k plus 1 to xn of k plus 1 will be equal to, see, the state variable will be a function of state variables and input. So the state variables will be multiplied by this matrix, that is A matrix, that its elements are a11, a12, etc. up to a1n. Similarly it will go to an1, an2, etc. up to ann. Next matrix is x1, x2, etc. up to xn plus b11, b12, b1m. Similarly it will goes to bn1, bn2, bnm, and it will be multiplied by u1, u2, um. So we can say that this is a function of state variable and input variable. So here we can represent this as a x of k plus 1 equal to a into x of k plus b into u of k. So this is the representation. So this is the state equation corresponding to the discrete time system. Okay, here x of k is the state vector of order n by 1. This is, okay, x of k is state vector of order n by 1. U of k is input vector of order m by 1. And A is called the system matrix of order n by n, and B is called the input matrix of order n by m. So this represents the state equation of the linear time invariant discrete time system. We know that in the case of a discrete time system we are representing it in the state space representation by using state equations and by output equations. So now we have reached up to the state equation. Next we want to write the output equation. So for that we are considering that output y will be the function of state variable and the input. So the output at any discrete time instant k are functions of state variables and inputs. Hence we can write the output equations, difference equations as y1 equal to, output can be written as a linear combination of state variable and input. So y1 equal to c11 x1 plus c12 x2 plus etc. up to dm1 m um. Similarly we can write the other equations also. And here c11, c12 etc. are quotients. Similarly d11, d1m etc. are quotients. And we can write this in the form of a vector matrix form. So we can write it as y1, y2 etc. up to yp will be equal to c11, c12, c1 and etc. It will goes to cp1, cp2 etc. up to cpn. Next matrix is x1, x2, xn. Next is D matrix and next one is U. So we can write this equation as matrix equation as y of k equal to c into x of k plus d into u of k. See, you may remember the equation in the case of continuous time system. There are also an equation that is y will be equal to c x plus du. That was the equation. And in the case of state equation, their equation is x will be equal to ax plus bu. That was the equation at that point. Okay, you may remember that equation. So here the equation is this one is the output equation. In this x of k is the state vector of order n by 1, u of k is the input vector of order m by 1, y of k is the output vector of order p by 1, c is the output matrix of order p by n, and d is the transmission matrix of order p by m. So this is the state space representation for the discrete time system. So state space representation contains state equations for the discrete time system and the output equation for the discrete time system. So we can together write the state model as x of k plus 1 equal to a into x of k plus b into u of k, that is state equation, and y of k equal to c into x of k plus d into u of k, that is the output equation. So this is this discrete time system state model. And here it is better to compare this discrete time system with a continuous time system, so that you can easily write the equations. So next, this we can picturize the state model in terms of diagrams. So that is called the state diagram of the discrete time systems. It is similar to that of the continuous time system, and in that case also there is state diagram, and basically we can represent the state model of a system or a control system by using state diagrams, and we are using a signal flow graph or block diagram representation in order to picturize the state model. So basic elements in both these cases, block diagram and in the signal flow block diagram, are basic elements of the state diagram are scalar, adder and unit delay. In the case of continuous time system, it was scalar, adder and integrator. That was the basic elements. Here scalar, adder and unit delay elements are the basic elements of the state diagram in the case of discrete time systems. And scalar is used to multiply a signal by a constant, and adder is used to add two or more signals, and unit delay element means that it will provide a delay for the signals passing through it. That means this element will delay the signals passing through it by one sample unit. So here different elements are scalar, adder and unit delay, and block diagram representation is shown here. So here input signal is x of k, that is a discrete time signal. So this is a scalar, so it will be multiplied to input signal. So we will be getting a into x of k at the output. And in the case of adder, it is represented in this manner. So here the discrete time signals are x1 of k and x2 of k. We are adding these two signals by using this adder. So at the output we are getting x1 of k plus x2 of k. Unit delay element is represented by Z inverse. This is an important notation. And here input is x of k plus 1, so that it will be delayed by the Z inverse or delay element. So we will be getting x of k at the output. That means it will be providing a sample unit delay. Okay. So these are the block diagram representation. When coming to the signal flow graph representation, we are representing the signal as each node, that is first node and second node. At the first node input is coming x of k, at the second node output is going, that is here the scalar element is shown above the arrow mark as a, that is output a is into x of k. Similarly adder is represented by joining of the two line points, and here there will be different nodes. First node represents input node, that is x1 of k is the input, and other input is x2 of k, that is represented by another node. So these will be added, means those lines will be joined at the same node, and here the scalar element is 1 and 1, and at the output node we will be getting the sum of these two discrete time signals, that is x1 of k plus x2 of k. Next is delay element, it is represented as Z inverse above this arrow mark, and here the input is x of k plus 1 and output is x of k. In the case of continuous time system also we are representing the same state diagram representation, except that there is no delay element, there is only the integrator. You may remember that, and you know the input to the integrator is a differential equation d by dt form, and output will be the original signal. So here it is delay element and input is x of k plus 1 and output is x of k. That is the only difference between the continuous time signal and discrete time signal case. And we can picturize it by using block diagram and signal flow graph. In the block diagram you can see, you may be familiar with block diagram in the first module session. And these boxes represent the scalas, and this is the adder, and this is the unit delay element, and this represents the feedback path. So this feedback will be added here, and you one point you should remember that the input to the Z inverse element is x of k plus 1, so that it will be delayed by 1 unit, and at the output we will be getting x of k. So the same block diagram can be represented as a signal flow graph in this. So each node represents the signals. First node u of k comes here, the notation is u of k not u of t, that was a mistake. U of k comes here and b is represented above this arrow mark b, and the next point signal is x of k plus 1, so it is marked here, and here the signals coming from b and other one is coming from the feedback path, so feedback path is marked here. Next element is delay element, it is represented as Z inverse, and the next node is x of k. Next scalar is c, next point is adder, that is shown here. So the signal at this point is y of k, and here also a signal coming from the input node, that is scaled to d. So this is the signal flow graph and block diagram representation for the discrete time signal. So this is all about this topic. Thank you.